Today, we are tackling something really critical. How do we get reliable results when we're analyzing time series data? Especially when we're hunting for trends. Our goal is basically to give you the shortcut to understanding how statisticians get around the biggest trap in this whole field. And that trap, it's assuming every data point is independent. That what happens today has nothing to do with yesterday. In time series, think stock prices, climate data, CO2 levels. That assumption is almost always wrong. The present depends on the past. We're going to unpack how that very dependence breaks some of our go-to statistical tools and, more importantly, how some clever fixes save the day.
That dependence is really the absolute core of the problem. When you take classical statistical tests, the ones designed for independent data points, and you apply them to time-dependent data, well, you immediately hit what we call the dependence effect. What happens is that the serial correlation, the connection between points in time, artificially boosts the significance of your test results. So you end up with a ton of false positives. Actually, it might just be noise that looks important because your test couldn't handle that temporal link. We absolutely need methods that preserve that dependency structure.
Okay, so let's start with the usual suspects. The classic tests most studies reach for first. They're mainly looking for simple trends. First up, the student's test. That's the one for spotting a linear trend, right? A straight line. The underlying model is pretty simple. Is the value changing predictably over time? The hypothesis is really just asking, is the slope of that line zero? Is it flat?
Exactly. Is the line flat? That's the question it asks. But, and this is the big but, the t-test assumes the errors, the random bits your line doesn't explain are independent and uncorrelated. When your data is autocorrelated, which time series data usually is, that core assumption is just broken. So the test, it's really not reliable for dependent data. Its inability to handle autocorrelation means that the value it spits out can be, well, basically meaningless sometimes.
Okay, so the k-test is out for dependent data. What if the trend isn't a straight line, but it's still consistently going up or down, say always increasing? Then we often turn to the non-parametric option, the Mann-Kendall test. It's rank-based, designed for monotonic trends that always move in one direction.
It is useful because it's a bit more flexible. It doesn't demand a perfectly straight line. It works by comparing every possible pair of data points and counting how many suggest an upward versus a downward movement. But here's the catch. Even this test, this rank-based one, it fundamentally assumes the observations are independent.
So we're still stuck with that dependence problem.
We are. And it leaves us with two really big problems with these traditional methods. First, that dependence effect we've been talking about, the inflated significance. And second, these tests are just too simple for a lot of real-world data. They can't handle sudden shifts like change points or regime changes or trends that curve in complex ways. Those things violate the basic linear or monotonic assumption.
Right, which naturally leads us to the fixes. When a core statistical assumption is basically guaranteed to be violated like independence in time series, we often don't just throw the test away, we adjust how we figure out its significance. And that's where bootstrapping comes in. The core idea from Bradley Efron back in '79 is actually quite elegant. If you don't know the true underlying distribution of your data, you can sort of reconstruct it yourself. You do this by resampling your original data over and over, maybe thousands of times, with replacement. Each time you recalculate your statistic, like the trend slope. This whole process gives you an empirical a bootstrap distribution for your statistic. You can then use that for inference, like finding confidence intervals.
And that works beautifully. If your data points are independent and identically distributed, like measuring heights in a random sample, shuffle them however you want, the average height calculations still make sense. But here's where time series throws a wrench in the works. Standard bootstrapping, it fails immediately. Why? Because resampling individual points completely shatters the time order. It destroys the dependent structure.
The temporal melody, I like that. Explain that a bit more.
Think of it like music, exactly. The sequence of notes, their relationship over time, that's the melody, that's the dependent structure in your time series. Standard bootstrapping is like taking all the notes from a song, throwing them into a hat, and then pulling them out randomly to play them back. You technically have all the original notes, but the rhythm, the connections, the song itself, it's gone. Utterly destroyed.
Oh, okay. So you lose the crucial context.
Precisely. So for time series bootstrapping, the objective isn't just to replicate the distribution of individual values. It has to replicate, or rather preserve, that temporal dependence structure. We need methods that keep that melody, that sequence, intact during resampling. Only then will our bootstrap test statistics behave like the real ones would under dependence.
Okay, so we need specialized methods to handle this melody preservation. And there are two main approaches, right? Let's start with the one that sounds like it tries to keep chunks of the melody together, the block bootstrap.
That's a good way to put it. The block bootstrap is pretty intuitive, actually. It's designed for general stationary time series. Instead of picking individual data points or notes, you define blocks, consecutive chunks of data of a fixed length. Then you resample these entire blocks, often overlapping ones, with replacement. By resampling whole blocks, you automatically preserve the dependent structure within each block. You keep those short musical phrases intact.
Okay, that makes sense conceptually, but how do you pick the block length? That sounds tricky.
That is the major practical hurdle. The block length is the critical tuning parameter. The literature points out there's a real lack of reliable automatic methods or even good diagnostic tools to tell you if your chosen length is appropriate. It often involves some trial and error, maybe some sensitivity analysis. It can be a real headache.
Right, a classic case of fixing one problem but creating a new tuning nightmare. Okay, so what's the alternative? You mentioned the Sieve Bootstrap. That sounds more refined.
It is in many ways. The Sieve Bootstrap uses a different philosophy. It's especially suited for series that can be well approximated by a linear autoregressive process, an AR model. Think of the AR model as acting like a filter or a sieve, or maybe even better, like those noise-canceling headphones you mentioned earlier.
Noise-canceling headphones for data. I'm intrigued. How does that work?
It's essentially a three-step process. First, you fit an AR model to your original time series. This model captures the predictable part, the autocorrelation structure, the music. What's left over after fitting the model are the residuals, the errors. And ideally, these residuals are now approximately independent, like the background static the headphones canceled out.
So you've filtered out the dependent.
Exactly. Step 2, you take these residuals, which are now roughly IID, and you resample them using standard bootstrapping. That's fine because they're independent now.
Yeah.
Step 3, you feed these newly shuffled bootstrapped residuals back through the estimated AR model, the filter you built in step 1. This generates a whole new bootstrap time series, but one that inherently has the same kind of dependent structure as your original series, because that structure was imposed by the AR model itself.
That seems much more elegant. The advantage must lie in how you tune it then.
Absolutely. The key tuning parameter isn't some arbitrary block length. It's the order of the AR model, basically. How many past time points influence the current one. And that's much more interpretable. Plus, we have well-established statistical criteria like AIC or BIC that can help select the AR order automatically, adapting to the data's specific dependence.
Data-driven.
Right. That adaptability is a huge plus. And it's why both the t-test and the Mann-Kendall test have been successfully modified using the Sieve Bootstrap approach. It gives you much more reliable results, like corrected p-values, that properly account for the serial correlation. Okay, so we've tackled the dependence issue for simple linear or monotonic trends using bootstrapping. But let's be honest, the real world often isn't that simple. What if the underlying trend isn't just a line, but maybe it's curved? Like a U-shape or a quadratic or some other more complex smooth pattern.
Yeah, until now, we've basically been testing, is it flat versus straight, or is it flat versus always going up? If we want to check for a specific curve, we need a different kind of test altogether, don't we? The hypothesis has to change.
Precisely. When you're dealing with potentially complex trend shapes, the null hypothesis shifts. Now, it's that the trend follows some specific, smooth parametric function, maybe a constant, maybe linear, maybe quadratic, whatever you hypothesize. The alternative hypothesis is simply that the trend is not that specific function. It could be anything else.
How do you test that? It sounds quite general.
It is general, and it led to methods like the WAVK test statistic developed by Wang and colleagues. Conceptually, it's a pretty neat way to check if your assumed smooth trend is adequate.
Okay, walk me through the idea.
Sure. First, you estimate and remove your hypothesized smooth trend from the data. Let's say you hypothesized a quadratic trend. You fit that quadratic, and you look at what's left over the residuals. Now, if your hypothesized quadratic trend was actually correct, those residuals should just look like random noise around zero, no pattern left.
Makes sense.
The WAVT test then checks if those residuals are truly random. It does this by grouping consecutive residuals together in time into small artificial groups or windows. Then it essentially performs an analysis of variance, an ANOVA test on the means of these little groups. It's asking, do these chunks of residuals deviate systematically from zero?
So if the group means themselves show some kind of pattern, like bumps or dips, it means the original smooth trend wasn't enough?
Exactly. If those group means show significant structure, you reject the null hypothesis. You conclude that the simple, smooth curve you assumed wasn't sufficient to capture the real trend, which must be more complex. And importantly, this WebVK approach has been extended to handle more complex error structures too, like changing volatility over time, which is really common in financial or environmental data. Plus, there are data-driven ways to choose the size of those grouping windows.
Okay, we've covered simple trends, complex deterministic trends, and how to handle dependence. But there's another type of trend problem lurking, isn't there? Something more fundamental about the series stability. You mean stochastic trends, or what are often called unit roots?
Exactly. This is a different beast altogether. It's not just about the shape of the trend, but whether the series is fundamentally stable or unstable, whether it tends to return to a mean or wanders off unpredictably.
Right, like dropping a pebble in a pond. If it's stationary, the ripples eventually die down, the water level returns to normal. But with a unit root, it's like the pebble just keeps drifting further and further away, and the water level never really settles back. The whole system's variance grows over time.
That's a great analogy. A unit root process, a stochastic trend, means shocks or disturbances have permanent effects. The system has a memory that never fully fades. The main tool we use to formally test for this kind of non-stationarity to see if we need to difference the data to make it stationary is the augmented Dickey-Fuller test, the ADF test.
Okay, the ADF test. What's the core idea there?
Well, what's really interesting, and maybe a bit counterintuitive at first, is how the hypotheses are set up. The test uses an autoregressive model, but it looks at the change in the series. And the crucial part is the null hypothesis. For the ADF test, the null hypothesis assumes the unit root is present. It assumes the series is non-stationary.
Whoa, okay, so the default assumption is instability. The burden of proof is on showing the series is actually stationary.
Exactly. You're trying to find evidence against the unit root, evidence for stationarity. So if you run the ADF test and you cannot reject the null hypothesis, the statistical conclusion is that a unit root is likely present. The series is likely non-stationary.
And that leads to differencing.
Typically, yes. If you fail to reject the unit root null, you usually difference the series, look at the changes from one period to the next, and then you run the test again on the difference data. You might repeat this until you do reject the null, and that tells you how many differences were needed to achieve stationarity. That's the order of integration.
Now, the ADF test and related ones like the Phillips-Perrin test sound like they're doing something really difficult, trying to distinguish between a series that wanders forever and one that just wanders a lot but eventually comes back.
They are, and that's where they run into known issues. The biggest one is low power. These tests often struggle to reject the null hypothesis of a unit root, especially when the true process is stationary but just very persistent, meaning shocks die out, but very, very slowly. It's hard for the test to tell the difference between a true unit root, infinite memory, and near unit root behavior, very long memory.
So you might mistakenly conclude a series is non-stationary when it's actually just very slow to revert.
That's a real risk. And adding other deterministic components to the test, like allowing for a constant term or a deterministic time trend in the regression, tends to reduce the power of the test even further. It makes it even harder to reject the null.
That was definitely a deep dive. We've covered a lot of ground. We started with the basic tests and Mann-Kendall for trends, saw how autocorrelation essentially breaks them. Then we found the fix with bootstrapping using blocks, or the rather elegant AR-SIF method, those noise-canceling headphones, to keep the time dependence intact.
Then we moved on to testing for more complex, curvy trends with approaches like WVK by looking for patterns in the residuals. And finally, we tackled those fundamental stability issues, the stochastic trends or unit roots, using tests like ADF, while noting their limitations, especially around power.
I think the biggest takeaway for everyone listening is this. You simply cannot get reliable insights from time series analysis unless you face the temporal dependence head-on. You have to choose methods specifically built to handle it. It's not just about running a test, it's about running the right test for data where the past influences the future. And always remember, the conclusion you draw depends heavily on the specific question, the alternative hypothesis your test was designed to ask. And that brings me to a final thought for you to consider. We talked about the low power of unit root tests like the ADF, especially against those highly persistent stationary series. So when an analyst runs an ADF test and fails to reject the null, they don't find evidence against the unit root. What does that really mean in the real world? Does it prove the system is truly non-stationary, fundamentally unstable? Or could it just be that their test didn't have enough statistical muscle to distinguish it from a process that's almost unstable, but technically still stationary? Something to definitely chew on next time you see claims based on finding or not finding a unit root.